So today we will be talking about the false economy of OOP, and we just kind of give you a quick introduction. So I'm actually working on the Go90 team at AOL, which just a quick historical thing is actually AOL was purchased by Verizon last year. So it's the same Scala team that was actually under Verizon, and half the team was transferred to AOL. So I'm going to we're going to be talking about false economy of OOP, and this title probably gives you some ideas like about my perspective is so I am actually over time I've actually grown to be a fan of FP, and some might even call me a bit of a zealot, I guess. But I've actually started the first days where I started getting into programming, as back in the C++ days. I was actually really excited about object-oriented programming. So I've completely come full circle here, and the idea of this is to really give sort of a journey through the thought process, and take all of you along to see how I've arrived to this conclusion about OOP as a model for designing software. All right, so now the Scala language, which is obviously a focus of this conference, one of the main goals of the Scala language is to bring both OOP and FP together cohesively into one language. And so when it comes down to actually bridging the worlds, I would say that it's been a resounding success. I mean, all of us here, or many of us have been working in Scala for a while and have found it to be a great language for solving complex problems. And so just keep in mind that there's the objective of Scala to combine these paradigms together. I definitely see it as a success. And the focus here is really more about OOP by itself, because I mean, while you can write software now effectively using both paradigms, we have to answer a question, okay, should we be using OOP for solving a lot of our problems? And OOP has been around for quite some time. Simula 67 first used the notion of an object, and that's why many see it as where OOP sort of started. Smalltalk is a commonly language that people usually attribute as the first language to really dive into pure OOP as an approach. But over time, I'd say, as OOP has progressed in the industry, we have found ourselves with a lot of code base that have become really complex and hard to work with. And this is what has really led a lot of new startups to start adopting FP languages. And the hope really is to leverage the fact that the language has a lot more of a concise syntax, and maybe if we adopt a language that allows you to write code more succinctly and express concepts in a more I should say a concise form, maybe in the long run, some of the initial investments will be compensated for the cost the cost savings. But as time's gone on, I'm sure a lot of folks have heard recently some major companies have adopted Scala, have kind of said, oh, wait a minute, it doesn't seem like we've spent all this time trying to acquire talent, training people, and investing in the new tool chains that are required for using Scala. And you have some companies that are kind of sort of backing away, kind of wondering, okay, what, is this FP stuff just kind of a, sort of an esoteric thing that just doesn't really, is it really all smoke and mirrors? Is it just a fad? Well, FP actually predates OOP by quite a bit. And it has its roots in what is in branch of mathematics known as lambda calculus, developed by Alonzo Church. And this is really kind of an interesting revelation because, as I've started programming since the beginning of my career, even before that, just playing around, with languages in high school. OOP has definitely it's been talked about a lot as sort of like, oh, this is the ultimate way to model software. So this might be surprising to a lot of people. So yeah, once again, the Scala language, the tool chain is complex, and the realization that we have here is, well, okay, if you take FP and OOP together, are you really going to get the true benefits of using a functional language? And the answer is, and the reality is, there are fundamental problems with the OOP model. When you're trying to create a class hierarchy that models your problem, I'm sure many of you have ran into this. It can be really, humiliating may seem like a strong word, but it's true. You might be like, okay, this model almost works, and I make this change here, and it's not quite. It feels like you get the distinctive impression that you're not really fitting the problem very, very precisely. And usually when you do settle on a good design, you think that you've actually you might have it worked out so that you add features, you have some extensibility there, but it doesn't take long before it begins to collapse on its own weight. So this is not your fault at all. And I think this is the realization that has led me to take a more serious look at FP as an approach to focus more on, because many of the places I've worked at have actually ran into the same problems. I run into more people that run into the same issues. It's really common to think, okay, well, is there something I'm doing wrong? Is there something I'm missing? It's something we keep telling ourselves. But with OOP, that's where the problem is. And it really, if we were to summarize it, we're saying, okay, the contracts that are defined in your class hierarchies and how you use inheritance and composition, and composition, I should just say containment, because in FP we mean composition in a much more precise fashion. But the contracts that you're defining are not, they are vague, and really the instruments that are there of OOP are actually, they're not precise enough. And there's a lot of bouncing around between different class hierarchies, and this becomes a real cognitive load, where you're trying to decide, okay, well, if I use inheritance here, if I factor these classes out this way, and you spend a lot of time trying to design your class hierarchies. So, and then you go back to, sorry, this thing's not. And then you have design patterns, and I think we all have the Gang of Four book on our desks. And how many times do you really find yourself reaching for that and say, aha, okay, this is exactly what I need? Happens every once in a while. You get kind of close there, but doesn't really solve the problems precisely. So really, OOP, once again, OOP creates a false sense of understanding. It really does. You create an OOP model that fits your problem, and it almost fits it, and it kind of creates a sense of, okay, I've got this, and it doesn't take long. Sometimes it does. And over time, you find that your model is just, flexibility just isn't there. And this is where the false economy comes from. And I'll be revisiting that back as we look at our example here, which is optical tape machine. So here's our example. Say we have a company called Tapeco. They have a tape machine that, I know that's not an optical, that picture right there is not optical. I'm just pretend like it is. It has an optical head as opposed to a read head, audio head. But say you have an optical tape machine that reads a tape with color band segments, which may have gaps in them. And we can pull the machine to say, okay, what color is under the read head at this particular point in time? So it may be over a gap, there's no color there, or it's over color, and then we know what the color is. So we have to be able to check and see if we reach the end of the tape and compute a score for each color on the tape. So here we have a definition of colors here, and we have a tape machine I/O, which is provided to us from Tapeco. And this I/O is pretty simple. You can start the machine. You can check, say, okay, are we at the end of the tape, EOT? Or we can pull and say, okay, which color do we have? So it's an option because if it's over a gap, then it's going to return a none. Now, okay, now we're going to define our model of this tape machine. So we're going to need some kind of a tape reader, which is for getting the next color segment. We'll define this notion of a tape reader proxy to sort of abstract away the I/O. So we say we have one I/O, another I/O, we're gonna just have one here, but let's create a tape reader proxy. So common thing that would be done when coming up with an object-oriented design. And also we're gonna have our scoring system for segments and segment groups. And we're creating these notions because based off our business rules listed before, you may have you'll have different segments of different colors, and then you have groups of segments together because you may have you may have 5 magenta, 3 green. So we're going to group those together. So there won't be contiguous groups, but we're grouping them together since that's how we're doing the scoring. And okay, so here's the scoring business rules I was talking about. So we have a score assigned for each color. We have this notion of a segment group, which is going to be the count of colors that you have there in the color. We're going to have, the tape is going to have its own score as well. And then we're going to say that, okay, well actually a total number of segments based off our problem here is 10, all right? And those are the business rules. So we're going to define a tape reader, and we define this proxy. We're going to read the next segment. Now this is blocking. So when you actually get the tape reader and you get next segment, it'll block and actually return what the next segment's going to actually be. And then we're going to have a tape reader proxy, which this is where this will not be blocking. It'll pull for the current color that's under the tape. All right. Now, by the way, the difference of these are both options here. The first one will return a none if we're reached the end of the tape, and then the tape reader proxy, it returns none if it's not over color currently. So that's kind of a difference there. So we're going to define the tape reader I/O, and this is going to take the tape machine I/O as a member there. So this is abstracting over the interface here. Now you'll notice that we're creating an abstraction here, and we have to do some delegation here, and we're kind of creating this this functionality here that's specific to that for us is specific to tape I/O. But you see, we're kind of doing some fairly general mechanics here that could be abstracted out here, and you'll see that later on. So we have so right here we're actually creating a segment. It's how the scoring, the segment group, and then the scored color trait. Now, also we need to collect these segments and actually, read segment groups from these. And we do this here, by this way, defines the tape machine, which has to have a tape reader within whatever class is actually extending this trait right here. So now we have a tape reader machine impl. which takes in the proxy and extends the tape machine and actually implements the get next segment in here. All right. Now there's a few improvements we can do. We could say that some of the code inside, we can make this a bit more functional. Like a great thing here we can do here is we could use a SCHALA-Z task, or sorry, a SCHALA-Z stream process, where we actually say, okay, we're turning the segments into a stream. So it can be a stream of tasks of segments right here, where it'll wait every 2 seconds and actually output the next segments as it gets these, and it'll return exception when it's done to sort of terminate the process. So this is an improvement we can do tightly. But after doing that, and then of course here we're running it right here, just do like segments, or that's how you would run the process and then run the task within it, and do the grouping. So turn into a string, but we haven't really changed the, we're using FP sort of in the small here, and it adds an improvement at the fine-grained level. So okay, after doing all this, now we have this scoring thing that's going on. What's going on here? What is this scoring all about, really? I mean, we saw the business rules. What are we doing fundamentally? Well, we break this down mathematically. We have W number of magentas, X number of ambers, Y number of greens, and Z number of aquamarines. And we know that there's the total number of color bands is 10, all right? Well, if we just multiply all the numbers times 10, okay, and then we say, okay, we divide these all by 10, well, that's the same as this. It's an arithmetic mean. So all this we've done here is really, we've created all this extra machinery to completely obscure that we're just doing an arithmetic average. That's all we're doing. So, okay, well, we're still doing things, we're modeling things using OOP. We're going to say, okay, we're going to pass this color code through all the different colors, and we're going to go here and we compute the scores differently, and oh, wait a minute. Notice we had a segment class before. It's gone now. Now we just have color represented directly. So you start to notice that as you start representing the problem, you're starting to get the core mathematical definition of things, which is a simple arithmetic mean. Some of your OOPS abstractions start to go away. And you see that here where we have this tape machine implementation. Now, I mean, you see the only difference as we go from segment to a color here. The segment class disappears. We just don't need it anymore. All right? Now, let's say we want to modify this tape machine and add the support for representing shapes. Meaning instead of having like multiple color bands, well, we can still support that, but let's say we also want to support tape that has like a large rectangle on it, and we want to compute the midpoint of that rectangle as the score. Well, you know, okay, so we have to pull some functionality out of this tape machine. Now we have to create a colored tape machine. We have to have a tape with shape machine because we got to handle shapes now. And then we have to go here, we have to create a colored tape reader proxy, a tape with shape reader proxy. And now we have to create this this color IO and the reader shape IO, that branches out into separate classes. We're pulling some common functionality out. The tape reader IO has this in common, and we abstract it this way. But you know, to be really honest, this is code duplication here. It's not really, I mean, syntactically, you're improving things, but semantically, it's not, I mean, you have, you know, you're trying to fit your model towards a problem by creating these sort of various, what in this case are actual stub implementations, but in a much more complicated problem, and it could easily be a lot more gnarly than this. And then you find right here, it's okay, we have our segment group. That part actually is okay. I mean, here we're representing the color, the score for segment group and a scored shape by finding a midpoint within a rectangle. So now we want to do version 3. So we have another version here. We have a pull shape part. Now this is a version of tape where say we have a tape that doesn't have just a single rectangle in there, but instead it has some part of a bigger shape. It could be like a half circle, it could be a right triangle, it could be a square, but the whole thing is like one big shape, and we want to compute the score of that, which would be the centroid of the region. Okay? Well, how do we compute centroids of regions? Yeah, it's pretty simple, really. I mean, we do these both for the XY coordinates have to be done independently. You compute the sum of the midpoint of each part, multiply it times the average of each part, and divide it by a sum of all the parts. You do that for both X and Y. All right? Well, all right. Sorry about that. Spoiler. So we created, so we have to create case classes for all the shape parts. We have to modify all the tape machine reader proxies, and we need to implement collecting of shape parts. It's going to be similar to colors, but different enough to make it annoying. Then we're going to try to, okay, how am I going to pull some common functionality here? So, and of course add the centroid computation. So, what is it you do here? I mean, what's it giving us? I mean, honestly, it's giving us more code to write. It's giving us more abstractions that leak. And why I say these abstractions are leaking? Because every time we're adding a proxy, or we're adding a new version of the tape machine, we have to add these other abstractions of other subclasses. Like, okay, are we really factoring things out separately here, or just kind of doing some syntactic representation, manipulations? I mean, the abstractions are not really well defined. They're not self-contained at all, so they're very leaky. And as I showed just with the arithmetic mean, we were completely obscuring what was really normally a very simple mathematical thing, and completely obscuring that. So all in all, OOP is it's a blunt instrument. It's clumsy, not very precise, and what guarantees are being really offered here? I mean, you're not really defining any rules that the compiler is going to help you with. You're just sort of grouping functionality together and factoring it out in a certain, just sort of rather arbitrary way. So, and what I talked about before, where I said you can fix certain pieces and make it more functional within your structure. Well, why do you want to do that? Because I mean, now you're effectively quarantining your FP usage in tight scopes, which you should do that with mutability and effectful behavior, not with FP. So it's kind of backwards in a way. So here we're going to show a new model that solves the problems of each of the three versions I talked about, but using instruments of FP, which are much more precise instruments. And it all starts with these three types right here. We have the duo type, which is simply represents two things, something of type A and B. Now that's a shapeless H list is what that is. And we'll represent that way because you'll see later it's kind of a convenient representation. We could have created a case class here that would have been fine. I mean, if you want to get precise about it, you're essentially creating some form of a product type. But we're using a shapeless H list here, as that seems to work pretty well. And we have a normalized type, where we say there's some input of some type, and we're going to read it in, and then transform it into a duo of A and B. Now, the reader, just to give you an idea what that is, that is a reader monad, which is a specialization of the Kleisli, which is really just a monadic function. That's what it is. And you'll see that you can actually compose these things in a lot more flexible ways than just as a basic function. And you'll see more in the example. But we have this normalization where we're saying, okay, anything that's in the duo AB representation, that's our normalized form, okay? Now we have an evaluate normalized where we say, okay, we have a value that's been normalized already. Now we're going to evaluate into some final result or an intermediate result. Well, no, sorry, it's a final result. The normalized form is also an intermediate representation. So yeah, so these are the three types. Now, there's not much hidden here at all. I mean, it's precisely, duo is just representing two things, and we have representation of a normalization and computing the normalization. That's all that's here. There's nothing hidden from view. Now we're going to abstract a duo plus, or plus star, what do you want, whatever you want to call it. It looks like a plus operation via monoid. Now, a monoid is, it represents, it has two operations. Scala Z refers to them as zero and append. Strictly speaking, append should, you probably just call it an operation because it's for combining two of one thing and giving you that same type of thing as a result. But it's very often used in a context for appending. I can give some examples, like the monoid of integer addition would be 0, would be the number 0, and append would be adding them together. You could have a monoid of integer multiplication, where the 0 would be equal to the number 1, all right? And append would be multiplying them together. So 0 is 1 in that case because multiplying 1 times a value is going to give you the same result. And it turns out that that's actually one of the rules here for monoids, where you're saying that you multiply the identity times the value. You should get the same thing as multiplying it, you know, in a different order or the value itself. Then there's also associativity here too, which the two examples I gave you, plus and multiplication, follows this as associativity rule. So your monoids have to follow those rules. And once they follow these rules, then you can have this abstraction here, which for the case of duo, we're treating both components, we're treating the components together because I mean that although they're abstract, duo AB is abstract, we want to create a monoid that says, okay, well, the A's can be combined together and the B's can be combined together, all right? This is very abstract, but this applies to all the problems that I showed before in the OOP design, and they will all fit this model very well. All right, does that make sense? So now we have what is essentially the meat of our computation here. It's known as the reduce method. And this reduce method actually ties everything together. And it assumes that you have a monoid of duo AB, all right? It also assumes, of course, that you have an F which is foldable, which you can do the fold operation, which is for combining values together in some fashion. And then we're saying that, okay, F has a functor as well. And of course, we have some normalization available to us that'll go from input to a duo of AB. And an evaluate normalize, that'll go from the duo AB to some E result, and then reduce, the result will be E. So this is for doing our computation. And this, it's kind of funny because it's really a one-liner, but there's 5 lines of type declarations. Now, what's interesting about it is you get this wrong, it's not going to compile. That's your error case. So you know if you got this right, you know it's actually going to, oh, I see we have a question here.
Yes, may I pose a question to the crowd here? Because Brian and I discussed this code, and we're curious, can you actually implement this and it compile any differently? Like, can you actually make this compile with anything but this or triple question mark?
No.
Because with the types, yeah,
You can't.
You actually cannot get it wrong.
Right, you can't get it wrong. The type system is completely, you're implementing this on the rails completely. And you define your types in this fashion. This method right here is going to require all of these to be available because, well, what are we doing? We're taking a values of I, type input, F of I, it's a bunch of values. F could be a list, it could be a set, it could be an option, anything that is a functor and a foldable. It takes those values, it maps them to norm, which is the normalized reader, which we defined earlier. So what is it doing? It's actually normalizing all your values. Now once we have all the values normalized, we're going to fold them using the monoid. And then you evaluate them and you get your E. All right? So that's all this does. That's everything right there. And we're using a functor, so I feel obligated to show you that the functors have rules as well. You have the identity rule, which says that if you're doing a map over a functor f, and the function you're using is an identity function, which says, okay, whatever input is the output, it should equal the same. It should be the same. It should be a no-op. That's all that says. And then if you were to say I have a functor and I'm going to map it using these two functions composed together, that should be the same as mapping one and then composing it with the result of the other one mapped. So really you can represent this in code very simply, where it's like, okay, you have your functions, you compose them together versus like do a series of maps. Now if you broke these rules, I think it's pretty easy to see that you have a functor that's just really irritating to deal with. I mean, it's a bad API. It's sort of like a microcosm of what happens when you have like a really bad class hierarchy where things are just not composable. And FP forces you to follow, it forces you to use these rules and compose solutions by combining them together. So, okay, now we've defined all the machinery we need to do an arithmetic mean. And we're going to create a case class called index sum, where we say, okay, we have a sum of all these values and a count of how many values there are. Now we have an evaluation result saying the result's either an error or a double result. Well, let's create a lift int. We need a normalizer. We need to be able to normalize these index sums into a duo AB, which in this case is going to be duo int int. Or sorry, duo int double. Now there's some neat shapeless machinery we're using here, where we're saying, okay, we have this index sum class, but remember, a duo is not a case class, it's a shapeless HList. So this generic index sum.to, that's a handy feature in shapeless where you can take an arbitrary case class and convert it to an HList. Okay? Why do we do that? Well, we want to have our nice named class that we use on the outside, and we want to internally represent things as HLists. A very common use case for shapeless. So we normalize everything in a way such that we say if we have, like, say, the number 5, we normalize it by lifting it into this form, what's going to be 5, 1. Why do we do that? Well, we're computing an average. You lift a 5, you want to say, okay, you have one of them. So now you have 5 and 1, you can compute your average easily. You just divide them. So then we want to evaluate the mean. And that's exactly what we're going to do right here. We're going to say, okay, we're going to evaluate this normalized form, the duo, and we're going to do it we're going to create a reader right here, which is a reader monad, and saying, okay, we have an index sum and count. If count's 0, well, you have a divide by 0, so that's an error. That's why we have this eval type, which by the way is a disjunction, that is actually known as a sum type. We're saying it's either this value or that value. Very commonly used for error conditions. That's how I'm using it here. So if that's an error condition, you get the exception. Left side, that's why the dash is there. Right side, you have an actual value, you can divide it. You're doing your average right there. And then we compose it with this other reader that's all it does is really converts this thing into a duo. And we need to do that because the evaluate norm, it expects a duo, which once again is an HList. So you have to compose it with this reader that does the conversion. That's why we use readers to begin with, by the way. It's real easy to do that. I mean, we could just say that, okay, we have our meat here, which uses this nice index some type for us, and then compose it with something that converts it to a shared representation that's used with the rest of our code. Now, it turns out, what if we want to do weighted averaging? It's really easy to do that. I mean, we just need to add this to all the code that we already have. It's a weighted integer, where we're saying we're creating a new normalized type that says we have a value and a weight. And we're going to lift it by saying, okay, the weight times the value in 1. That's it. We've just added support for weighted averages. We want to compute a median. We can do the same thing. We can actually, we're going to define a values class. This is a little interesting here in that we're actually not using the second part. They're saying put a unit in there. We just need the first half of the duo. Because all we're going to do here is when we lift this thing, single values get turned it into a list of values of just one value. We're going to do compute the median. This computes the median right here. But once again, we don't need the second value there. But it all fits the same form. Centroids, a much more complicated example, but it also fits this form. We have different shape representations. Now we wanted to be a little bit cute here and like add some little thing where we say, okay, well, a square is really a rectangle where the side is the same. A rectangle is actually 2 right triangles. So we're kind of doing some composition of shapes here. And I introduced the notion of a trampolines here as well, just because I mean, if you implement this using recursion right here, you could just use recursion, but it's not stack safe. You have a complex shape, you could blow the stack building a really complicated shape here. Well, guess what? To implement in the stack safe fashion using a trampoline, very easy to do. It's very similar. I mean, look at the code. You just represent as a trampoline type. Since the trampoline type is underneath covers, it's actually a free monad, but you don't have to keep that in mind when you're using this. I mean, you just know, okay, I'm building a trampoline. I'm essentially saying that this is what's returned and this is a value that's going to be suspended on each level of our sort of imitated stack that's going to be on the heap. And then we can write all these different shape functions, okay? So that takes care of all the shapes. How far did I go ahead here? All right, and then we have all the operations we're saying, okay, we're gonna have our normalize right here, which lifts the shape. And since really computing a centroid is another form of an averaging, it really is. We're doing the same sort of thing where if you remember the formula before, you have for each of the different shapes, you have the midpoint in the area, and all those are collected together. They're summed together, okay? That's our monoid doing the heavy lifting for that. And then we have this divided by a total summation of all the areas. And that's the second part of the duo where that's computed. So here we can evaluate the centroid using the same structure. And since everything is precisely defined we've defined a monoid of duo AA, well, there's nothing to stop us from having a monoid of duo, big decimal, because we have the definition of a monoid of duo, big decimal, and we also have a monoid of duo, big decimal as well, because it's a recursive definition. The definitions are already there. We didn't have to define each of these different levels of recursions. It just works, because all the monoid definitions are available. And by the way, I'm using big decimal because a monoid over doubled does not follow the rule of associativity. That's because of floating point arithmetic. So you have to use big decimal. So I have an important thing to consider there. And so that's how you compute the centroid in this fashion. So we're following the same structure and we're able to solve all these problems with the same code. So once again, abstractions in FP, they're more precise, but they're less familiar. I mean, there's a lot of new concepts to learn, And believe me, I'm still learning a lot of them myself. I mean, it's a very interesting world of a lot of different representations of things that we've seen already in our code, and just probably have just been agitated, like, gosh, there's got to be a precise way to represent all these different patterns. And I'm sure you've seen that. I mean, we're trying to build object-oriented code and haven't been quite satisfied yet. Well, you know, Scala Z, CATS, these libraries are collections of a lot of these very concepts that we've been looking for, you know, since we've begun programming, to be honest. And it's really important to understand that familiarity is not the same as simplicity. Okay? I mean, there's a learning curve, no doubt. There's a learning curve. I mean, it's to learn all of these concepts takes time, patience, and, you know, talking with, you know, folks in the community and you know, just sharing ideas and knowledge about these different tools that already exist. And that's sort of the beauty of FP, is that you're not just inventing abstractions out of thin air. You're standing on the shoulders of giants and using abstractions that have been around, you know, since the beginning of, when we were at, going back and, study various branches of mathematics. I mean, we're talking about real fundamentals here that we have a way of taking advantage of these fundamentals. So this is really an interesting thing that I've learned just completely through my own discovery and, journey through learning more about FP, is that there is no FP rabbit hole. That's a complete illusion. And the reason why I say that is because what happens if, what's the worst case scenario as you try using these different concepts and combine these together? What's the worst case? Your code won't compile. So, okay, well, what do you do then? And you say, okay, well, what I do wrong is to start, doing some, Stack Overflow searches and looking at some documentation and, I mean, how did I learn the free monad? I looked at like 5 different documents and compared all of them and just did my own example that was different from all 5 of those. And finally started piecing together this is what a free monad is. I mean, it's sort of a messy, rough process to kind of figure all this. But once you start seeing how the different pieces fit together, it's pretty exciting. And OOP, on the other hand, you don't have rabbit holes, you have gravitational singularities. So you can fall in a black hole and not even realize it's like, I mean, okay, I'm solving this, I got this working, but then you have to add this feature layer later, and it's just, you end up with this code base that's just a real tangled mess. And I mean, we're humans. I mean, it's hard to keep all that stuff, all of our heads, all that stuff in our heads at one time. And that's why I think programming with FP is really an act of humility. I mean, there's no reason to be, to humiliate ourselves in trying to structure things in these strange ways when we can just, okay, there's much more precise ways to define the different pieces of what we're trying to build here. And that's really the central idea. Now, I really do think that we are in the most turbulent time for FP in the software industry. And the reason why I say that is because, I mean, there's a point in time where FP was all in academia. So it hasn't really been tapped by the industry yet. Well, now people are starting to get excited about it. And you see a lot more companies using tools of FP, Scala, Clojure, a lot of the FP languages. And I think the excitement right now has outpaced sort of where a lot of us are in understanding these core principles. I mean, all of us have a lot to learn on all this, and that's why I say turbulent, because excitement is there, There's still a lot to learn, and I think there's a lot of frustration. That's why you see some of these companies that will adopt Scala, then kind of like, oh, well, what did we get ourselves into? And it's really, you know, it's just a point that we're at in the industry right now. And as a result of that, really, I mean, this is kind of the silver lining. I mean, there's still time for us to learn. And it's not, you know, and, you know, at any point where, you know, where folks are at right now, you're pretty much ahead of the game, I would say. But to be really honest, I really do believe that there's a point where this is going to take off in the industry, and it's going to reach a point where everybody's using FP in some form or another. You know, it may not be, you know, it may not be in Scala Z or CATS. It could be a different language. It seems very likely it could be Scala. I mean, just looking at how much interest is in there now, many folks are, you know, working in the Scala language. Seems very likely. But I really do see it as becoming a required and essential part of building software in the decades to come. And here's a tweet that I posted back in March of 2016. And this is in response to people I've heard say, like, oh, all this pure FP stuff, it's not going to scale on large teams. And no, I'm sorry. I mean, I work at, you know, pretty large company, and we've seen the opposite actually demonstrate in reality. So yeah, I mean, I really see that this being the reality down the road. I mean, I don't know when this will be. I mean, none of us knows. I mean, we can't really pretend to know exactly when, but I mean, it's really inevitable. So, all right, that's the end of my tape here. So I think we have a little bit of time for questions. Questions, anyone?
I don't actually have a question, but a comment that I believe you said set was a functor, and
Oh, sorry, you're right. No, yeah, okay, that was totally, yeah, right. Sorry about that. It's not. Yeah. Anybody? No? All right, well,